After studying this module, you shall be able to know about the electron transfer reactions, know the calculation involved in electron transfer reactions. You will learn about the dynamics of electron tunneling in the Marcus theory and know about the Marcus cross relation. Introduction. There are various types of electron transfer reactions. Since the later 20th century, the field of electron transfer process has grown exponentially. An example that can be stated here is transfer of an electron from the reduced form of reactant to the oxidized form of reactant in solution. Both organic and inorganic systems can undergo electron transfer. Also, the electron transfer reaction can occur in solution and in those reactions which happen through interface in complex biological systems. The electron transfer takes place in both the systems, inorganic and organic, in reaction that take place in solution and those which happen through interfaces in the complex biological systems. Let us assume a self-exchange reaction which is the simplest of all electron transfer. MnO4 2 minus plus MnO4 minus giving MnO4 minus plus Mn4 2 minus. In aqueous solution, the rate of reaction of a large number of central metal atoms and ligands can be calculated experimentally by marking the metal in a particular valence state by a tracer which can be radioactive atom and following the appearance of it in other valence state. R.A. Marcus was awarded by the Chemistry Nobel Prize in 1992 for his contribution to the theory of electron transfer reactions. According to him, the main idea underlying this electron transfer theory is the twofold and can be demonstrated using reaction 1. When the electron jumps from the MnO4 2 minus to MnO4 minus, which happens quite rapidly, that the electron in both the reactant as well as the solvent molecule do not have time to move in that transitory instant, since the atoms are much heavier than the electrons, that is, the transfer must obey the Franck-Condon principle. This limitation has major significances. The solvent dipolar molecules being incompletely oriented towards the ions and much more towards the highly charged ions. Hence, each of the newly formed ions in reaction abruptly find itself in a wrong solvent environment. If the electron transfer were to take place in the absence of absorption of light, this mechanism would violate the law of energy conservation. A necessary rearrangement of alignment of the solvent molecules in the neighborhood is required for a thermal electron transfer to continue. With a suitable fluctuation, both the Franck-Condon principle and energy conservation should be satisfied simultaneously, while the energy conservation principle would be violated in the lack of this variation. Marcusan origination of the electron transfer theory in 1956 found a way for finding the required redistribution and applying it to describe the transition state and to find out the reaction rate. Firstly, he used a dielectric continuum model for the solvent and calculated an expression for the free energy of such a dielectric continuum undergoing variations. This G was calculated by discovering a reversible path for creating such a non-equilibrium state of the solvent with an arbitrary dielectric polarization function at every point in the system and to find out reversible work to form that state, so as to find the dielectric polarization function characterizing the transition state of the reaction. Free energy was diminished subject to the constraint that the transition state was an ensemble of configurations of the system that contained the Franck-Condon principle and the energy conservation upon electron transfer. Like this, an expression for the rate constant of the reaction was found. Now we'll learn about the mathematics of electron transfer. The electrons are assumed to be transferred from D, which is a donor species, to A, which is an acceptor species. D and A should diffuse together through the solution and must collide to form a complex dA, which consists of the donor and the acceptor that are separated by a distance r, which is the distance between the edges of each species. Considering that dA and dA exist in equilibrium with each other, we get the relation for rate constant, which is equal to the concentration of complex dA divided by concentration of D into concentration of A. The electron transfer occur in dA to yield D plus and A minus. The rate of reaction can be given as equation 3. The D plus A minus complex then breaks apart and the ion diffuse through the solution. Marcus treated the electron transfer process from activated complex theory. We know that K is equals to kappa into nu exponential raised to the power minus delta G hash divided by RT, where kappa is the transmission coefficient, nu is the vibrational frequency by which the activated complex approaches the transition state, and delta G hash represents the free energy of activation. The theoretical expression for kappa nu and delta G hash can be calculated. There are two important concepts in the electron transfer reaction for Marcus treatment. The first one, the electrons can be transferred through a potential energy barrier whose height can be determined by the ionization energy of dA and D plus A minus complexes. Electron tunneling effect, the magnitude of kappa into nu. Tunneling is a only quantum mechanical occurrence. Its best known examples are in semiconductors and superconductors. The second point is structural rearrangements take place in the complex dA as well as in solvent molecules surrounded it before the electron transfer occurs. Delta G hash can be calculated by the energy required by such rearrangement and with the standard reaction Gibbs energy delta G naught. We have discussed how the Marcus continued to find out the free energy. Marcus presented that delta G hash is equals to delta GR naught plus lambda whole square divided by 4 lambda. In this equation, delta GR naught represents the standard reaction Gibbs energy for the electron transfer process, and lambda is the reorganization energy, which is the energy associated with the molecular rearrangements that occur so that the complex dA can accept the equilibrium geometry of D plus A minus. These molecular rearrangements consist of the relative orientation of the D and A molecules in dA and the relative orientation of solvent molecules surrounding dA. Dynamics of electron tunneling in the Marcus theory. We have already mentioned about the importance of Franck-Condon principle in electron transfer process. The Franck-Condon principle consists of electron transfers from one energy surface, which shows the importance of the energy of dA on its geometry, to another representing the energy of D plus A minus. We can represent the potential energy surface diagram for the two complexes by corresponding parabolas characteristic of simple harmonic oscillator with the displacement coordinate corresponding to the changing geometries. This coordinate indicates a shared mode of donor, acceptor and solvent. Since as per to Franck-Condon principle, the nuclei do not have time to move where the system goes from reactant to product surface due to the electron transfer. the electron transfer can take place only after thermal fluctuations carry the geometry of dA to Q star, the value of nuclear coordinate at which the two parabolas intersect. The Gibbs energy surface of the complexes dA and d plus A minus involved in the electron transfer process. Kappa nu is the factor in equation 5 that measures the probability of the system that will change from reactant to product at Q star through electron transfer inside the thermally excited dA complex. For understanding this process, we should consider the effect of rearrangement of nuclear coordinates on electronic energy level of dA and d plus A minus for a given distance r between d and A. You can see in figure the mechanism of electron tunneling in electron transfer. Initially, the electron that is transferred occupies the HOMO, which is the highest occupied molecular orbital of d, and it is found that the total energy of complex dA is lesser than that of d plus A minus. You can see in figure A, the reorganization of a nuclei to a configuration is represented by Q star in figure B. The electron transfer become energetically possible because the uppermost occupied electron level of dA and the lowermost unoccupied electronic level of d plus A minus becomes degenerate. At a short distance r, the central mechanism of electron transfer is tunneling via the potential energy barrier. The length of the hurdle increases with increase in the ionization energy of dA and d plus A minus complexes. After the movement of electron from the HOMO to d to the LUMO of A, the system eases to the configuration and is represented by Q naught P as represented in figure C. Presently, the energy of d plus A minus is lesser than that of A, representing the thermodynamic affinity of A to remain decreases and for D to remain corroded. The electron tunneling rate is shown by a wave function xi d to the level as shown by a wave function xi a is proportional to the square of the matrix element, that is given by the expression where H is the Hamiltonian operator that describes the coupling of the electronic wave function. In cases where the coupling is weak, it is established by equation 7, where r is the H to H distance between D and A, and alpha is a parameter that measures the sensitivity of the electronic coupling matrix element to distance, and xi a into Hamiltonian into xi d is the value of electronic coupling matrix element where D and A are in contact. The exponential dependence on distance in equation 7 is basically the same as the exponential reduction in transmission probability via a potential energy barrier that one meets in tunneling via barrier internally. The rate constant for electron transfer can be calculated by equation 8, where delta G hash is given by equation 6. Suffix it to the state that it is appropriate only to practice with weak electronic coupling between donor and acceptor. Also, the term pi cube divided by 4 lambda RT raised to the power 1 by 2 exponential minus delta G hash divided by RT should be applied only at a large temperatures, since at low temperatures thermal fluctuations cannot bring the reactants to the transition state, and activated complex theory, which forms the foundation of electron transfer discussed here, falls to account for any electron transfer. From equation 6 and 8, we have equation 9 and a plot of ln k or log k versus delta G R naught is observed to be a downward parabola. From equation 9, it can be concluded that the rate constant for electron transfer increases as delta G R naught decreases, but only up to minus delta G R naught is equals to lambda. The reorganization energy. After reaching the maximum point on the curve, the reaction reaches a point at which the rate constant reduces as the reaction becomes more exergonic. Delta G R naught becomes more negative. The inverted region has been observed in a number of compounds in which the electron donor and acceptor are related covalently to a molecular spacer of known and fixed size. The variation of log KET with minus delta G R naught for a series of related molecules. The Marcus cross relation. The Marcus theory has magnificently clarified the mechanism of the outer sphere exchange reaction, such as that of shown in this reaction, where the star indicates a radioactive isotope of iron that acts as a tracer. For the outer reaction, Marcus provided an equation from the exchange rate constants for each redox couple involved and the equilibrium constant for the total reaction. The Marcus equation for the rate constant is given by the expression which shows K square is equals to F into K1 into K2 into K, where K1 and K2 are the rate constant for the two exchange reactions and capital K is the equilibrium constant for the overall reaction. The factor F is a complex parameter which consists of the rate constant and the encounter rate. It can be assumed to be approximate calculation. The Marcus cross relation provides the weighted average of the two rates of self-exchange. Now let us summarize. There are various types of electron transfer reactions. The electron transfer takes place in both the systems, inorganic and organic systems. According to R.A. Marcus, electron transfers occur so rapidly that the atoms in the reactants and the solvent molecule do not have time to move in the transitory instant, as the atoms are much heavier than the electrons. Marcusian origination of the electron transfer theory planned a way for finding the required redistribution, applying it to describe the transition state and to find out the reaction rate. The Marcus theory has magnificently clarified the mechanism of the outer sphere exchange reaction by giving the Marcus equation for the rate constant.